Alright guys, so this is problem number 59 from the same page 135. So this is a good time to pause the video and read the problem. It is right here. Okay, so you can see that I have drawn a second picture in the bottom, and the reason that I did it like this is because I just would like to have my center or the centripetal direction along the positive x direction. If someone is comfortable with the picture over here above the above picture, then he or she can actually work it out the same way as it is given. So the lengths of the strings are given 1.7 meter, and the vertical the rod is rotating, and the strings are tied to the rod with separation of 1.7 meters. So what it says is D over here is 1.7. Now I am working on the top picture, like the picture over here, 1.7, and this is a 1.7, and there is a 1.7, right? So if you have a triangle with all three sides equal, then you know the other characteristics of that triangle, right? Okay, so the first step is to draw the diagram. Well, we are done with that, and then the second step is sort of like, you know, setting the forces on the diagram. Now I am going to erase these lengths over here because I want to mark the forces over there. Okay, now the first force, the most important one, is the weight. We are done with that. And then over here we have a string, a stretched string, and there is a tension. I'm gonna call it FT1. And then down here you have another stretched string, and I'm going to call this FT2. So you see that triangle is a equilateral triangle, and the situation is more or less a symmetric situation. However, the forces that I put over there, upper string, down here I'm going to redraw the forces. I said it is FT1, and then down here I have it as FT2, and down here the weight straight down W, and these angles, all of these angles are 60 degrees, right? So do you think that FT1 equals to FT2? Do you think it is the case? Well, I don't really hear what you are saying, but if you say yes, that is incorrect. They are not equal to each other. Now FT1 is the tension on the upper string, FT2 is the tension on the lower string, and so at this point we are just have this moment frozen, and when the rod is rotating around, this object is making a circle in this form, and you know, there is a toy, I don't remember the name of the toy, but children I have seen using these type of toys, and it actually goes around a circle. The object is going around a circle like that, a horizontal circle, and then the center of the circle, if I mark it using the red dot over here, I mean the red marker over here, so that's where the radius is, I mean the center is. So this is the radius, and down here this is the radius, right? So so FT1 is sort of balanced by W and FT2. Therefore FT1 cannot be equal to FT2. So keep that in mind. So we have 1, 2, 3 forces, and I'm going to separate them and just mark the object over here, and then have FT1 like that and FT2 like that, and then W marked in this form, and this is the direction of the center or the x-axis in this case. So if I ask you to find the angles, what can you say about this angle? We earlier said that this is a 60, this is a 60, as well as this a 60. So this angle is a 30 degree, and this angle is also a 30 degree. So the problem wants us to find the tension in the lower string, and the magnitude of the net force on the ball, and the speed of the ball, and the distance. So there are four different things that we are looking for, and then at this point we can write down the given information. So here we go. Given information. Mass of the ball, is it given to us? No, it's not given to us, and we have L equals to D equals to 1.7 meters. Now luckily we have L and D equal to each other, but if I give an exam problem out of this, I will definitely change these distances. So you will have to use the right triangle theorems, Sokotova, to find the angle over here. Okay, in this case it is a equilateral triangle, so we are good. Angles are 60 each. Oh, by the way, the mass of the object is given to us 1.34 kilograms, and the tension in the upper string is given to us as 35 newtons. So here we go. Ft1, the upper string, tension is given to us as 35 newtons. So recall the recipe that we are using. So once we have all the given things marked, and once the force diagram is set up, the next step is setting up those tables. So I'm going to use the X table first. Let's go with the X first. And how many forces are there? 1, 2 and 3, right? Alright, so you have Ft1, I'm going to call it X component, and Ft2, going to call it X component, and W also, there's an X component. So Ft1 is already we know it is 35 Newton, and 35 cosine 30, and Ft2 we don't know, therefore you call it Ft2, and this angle is cosine negative 30. Don't forget it is in the fourth quadrant, meaning the angle is measured in the clockwise direction, therefore you are using it as a negative 30, and W is pointed straight down, and W is cosine 270. Alright, and then we are looking at the X component, or the direction in the toward the center. So if I extend this table just a little bit, and if I just add that A is C, this is going to be AC at this point, and it's going to be V square over R. So as I said, I'm not going to do the work for you. So 35 cosine 30, you can find it out, and Ft2 cosine negative 30, and then W is mg, but cosine 270 is a 0, so that altogether it goes to a 0. And then at this point, if you want to substitute for cosine 30 and cosine 30 over here, you can do that. Since it's going to be like crowded, I'm going to use a different color, and 35 cosine 30 is a 0.86, and then here you have Ft2 cosine negative 30 is also a 0.86, and there you have a 0. Alright, so now that we have the X component table is ready, I am going to use the first Newton's second law along the X direction right here. So we can actually get done with that. Fx equals to mass times Ax. So here you have 35.86 plus 0.86 times Ft2 equals to mass times V square over R. By the way, do we know R? Well, I am going to use the green to mark the distances. Now this distance, if I ask you what this distance is, this is going to be 1.7 divided by 2. And if I mark the distance over here, that's going to be 1.7, and the triangle is a right triangle. You see that? So if this is a right triangle, you should be able to find R, and that's going to be 1.7 square equals R square plus 1.7 divided by 2 square, and this is coming from the Pythagorean theorem. You can find r and you can substitute it in this equation if you like. And by the way, we know the value of mass as well. Okay, now on this side I am going to set up the y table. So here we go. Alright, so here we go. I actually have the force diagram also right next to me on the right hand side. So like last time, we can use ft1 along y direction, ft2 along y direction, and w along y direction, and also I am going to add ay. So ft1 is 35 sine 30, and here you don't know what ft2 is, and ft2 sine minus 30, and w sine 270. And like last times, here you have a the circle, and it is actually on a horizontal plane. There are no vertical motions along attached to this one. Therefore, I can say that there is no y component acceleration. So like last time, we are using sum of f equals to mass times a along y direction. So sine 30 is a half, so you have 35 times 0.5. I mean, if you like to fill the table over here and write down these things, that's fine too. So here you have a 35.5, and there you have ft2. This is a negative 0.5, and sine 270 is a negative, therefore you have negative w. W is mg, so you have negative mg, okay? And then here, let me substitute for all these things. So negative 0.5, I like to use my black pen again. Let me go with that. Negative 0.5 times ft2 minus mg equals to mass times acceleration. Acceleration is 0, right? So you have 35 times 0.5 minus 0.5 ft2, and m is 1.34 times 9.8 equals to 0. So using this, you can find ft, and I'm going to take leave all the numbers on this side, and I'm going to take ft2 to the other side. So you will have 0.5 times ft2 on the other side. So basically, you do the math, you do the calculations, and here you have 35 times 0.5 minus 1.34 times 9.8, and the whole thing divided by 0.5. So I have isolated ft2 on the left hand side. So we are done with ft2, and we have the answer for part A. So I just want you to find this as a number, and the answer will be in newtons. So you have to bring the answer to this question also to the class after the break, okay? And then the second part asks us to find the magnitude of the net force. Now clearly, the magnitude of the net force means the force along the x direction, because you guys saw that when we were using this equation up here, we were using Newton's second law along the y direction, and only on the left hand side we had couple of things, and different forces along y direction, but the right hand side set equal to 0. In other words, the net y component force, according to this equation over here, the net y component forces are equal to 0. Therefore, we do not have a net y component force. The only force that is available as the net force is the x component, or the force along x direction, or in other words you can call it the centripetal force, right? Same thing. I just don't need a summation sign for that. You can call it sum of fx equals to fc. So if you go back to the previous page and find out the equation that we have for the x component forces, you can substitute for ft2 and you can find the net force along fx. So basically, your equation on the other side would be this equation. That's what we used, and we have r, and we have m, but we don't know v square. However, sum of fx separately you can find using the table, and that would be the left hand side of the equation on the previous page. Actually, when you guys are watching this as a video, you don't really see this as a previous page, so you can go all the way back and find that equation and bring it over here. So just by memory, when I write it, you have 35 sine cosine 30 is a 0.86 and plus ft 2.86, and that's what you had. Now that you have ft2 that we found over here, this is our ft2, you can bring that ft2 over here and plug the numbers in and find the net force along x direction. Take it really slow. If you don't understand things right away, that's okay. I strongly suggest that you write these things down and work with me for the first time, and then the second time you can work alone. So the second part asks us to find the speed of the ball. Third part asks us to find the direction of f net. So the direction of f net is easy. So I'm going to answer that in the next slide. So the direction of the net force, as I said, it is easy, because if I draw this diagram one more time, here goes the rotating pole, and I'm using a different color now to show these two strings, and this is the mass, the attached mass. Here you have ft1, and we know that. Here we have ft2. At this point we know that as well. So the weight also is pointed out like that. So the ball is going around. Let me use a different color. The mass is going around, and it is uniformly circulating around this circle, and at one point you can see the mass over here, and at another point you can actually see the mass over here. That's how it rotates, right? So at all times the net force is pointed in the direction of the center. So part D answer is F net points in the direction of the center. Direction of the center, or you can call it direction of the pole, rotating pole, central direction. So this is how the pole is rotating. And if you go back to part C, part C asks us to find the speed of the ball. So the speed of the ball is involved in the first equation, where we had sum of fx equals to mv square over r, and sum of fx, that's the answer for part B. We found that, and we can use the answer from part B and put it over here. And the mass of the ball is 1.34, and v square we don't know, and the value of r already found. Using the Pythagorean theorem, and you can substitute the r value over here, and using all those things, and you can calculate v, and if you have all the SI units, the final answer will be in meter per second. Now, this is a very good exam type problem, and again I suggest you go over this very carefully, mark all the forces nice and neat. You can rewind the video clip and go back and forward, and if you have a question about the video or about the math we did, you can certainly call me or email me at any time. Okay, alright.